Hi, I am Hashim Motabagani, a computer science student from the Pennsylvania State University, sponsored by the King Abdullah University of Science and Technology Get to Student Program. This summer, I had the great opportunity to work at the Zoom lab in the Carnegie Mellon Robotics Institute. And I explored how can we accurately simulate soft robotic manipulators, specifically the DeltaZ had or the DeltaZ platform, using a MuJoCo physics engine. You would ask, why simulation? Couldn't we just build it? And I would say, probably, but that will cost a lot of money and time because building and testing soft robots will take time for 3D printing, it will be slow, and it's prone to trial and error, which will take a long time. And a realistic simulation can save us a lot of time and weeks of work to allow us to test designs virtually before having to implement them by 3D printing them. But you'd ask, why the DeltaZ had exactly? So a DeltaZ is a modular soft robot and in our model it's 3D printed with TPU95 limbs, a material that is soft enough to deform when they interact with object, but still strong enough to perform tasks. And those soft limbs give us a unique advantage: safety around humans, adaptability in unstructured environments, and the ability to grasp delicate objects. But softness also brings complexity, and the motion of soft object depends on the material physics, the contact forces, and the geometry of all the components of the robot interacting together. And without a good simulation, we're left guessing on how this design will behave until we printed it in real life and test it out, which, as I mentioned before, is a quite expensive process. But you'd ask, why MuJoCo exactly? And what is MuJoCo? So MuJoCo stands for multi-joint dynamics with contact, and it's a real-time physics engine. And since version 3.0, there were two key features that were introduced: Flex and FlexComp. In Flex, we were able to, for example, take the limbs that were already defined as rigid and have them in a section in the code called deformable, and we were able to define the youngest modulus and the edge damping at the contact solver to make sure it actually accurately captures the physics of a soft material. And FlexComp, we used it here to take the CAD file of the fingertip of the DeltaZ hand and also define the properties of it. And we needed to use and we used FlexComp and we defined it and we connected it as we did with the rigid model, but instead we had it defined as soft. And that's exactly what we needed for our simulation. We wanted to make sure that those components are defined with the properties that are as close as to our real life model. So as you can see in our figures right here's the DeltaZ hand, and all the greenish components are soft components that were defined, and also they match exactly what are here in the physical robot that we tried to test on. And we ran two specific tests, which are pressing down on a rigid cube. And to be honest, I just found a soft wooden cube in the lab and decided, why not use it? And we did the test with our rigid simulation, our soft simulation, and then the real life simulation. And we pressed down on a cube, and then we also pressed on the tip of the DeltaZ hand upwards. And as you can see, as you mentioned, TPU95 is still strong and able to hold up its shape, but it's soft and could interact. The deformation that was shown in MuJoCo actually reflected that. As you can see, the bending in the real life experiment is minimal. It's there, but it's minimal. The same goes here. What it did is that it looks like the limbs pressured down on the platform in the middle, and they went the level, like as you can see the difference here between the red part, which is the cube, and the light green part here has decreased a little bit the level, as if it was pressed down. But you can see here in the rigid, for example, those limbs just stayed there. The fingertip seems as if it broke into the cube itself. And here we could see, we would to a certain extent say that it showed a deformable kind of bending behavior. But here comes the gap, a huge gap that we found that needs to be addressed later on, which is when we asked to press up into the fingertip. It was accurate to a certain extent, where we could see some form of twisting, but the connecting points broke, as if it was connected by a rigid connector. And here comes the problem. You could see in our soft model, it twisted, but the connections didn't break. Here is the same thing. And here comes the challenge. This behavior should not have happened unless shouldn't have happened unless it's a rigid model where the connectors would break if they were bended. There's twisting you could see, but still there is some gap that needs to be filled. During my experience, I've seen that there could be extensions that are added on MuJoCo, and that could be a future work we could work on, is to program an add-on that is able to define connecting points as if they were all part of the same body, just like the TPU95 model here. As you can see, the hand is just one object. You might ask, have you tried to take the CAD file for this tip and define it as soft in MuJoCo? And I would say yes, we tried. MuJoCo was unable to define it as soft. It was exported as a rigid model just fine, but when we tried to define it as soft, MuJoCo was unable to. It just kept on loading screen with nothing. So that's our gap, and that's the summary of my project. Before ending, I would like to thank my mentors. I would also like to thank Dr. John Nolan, Rachel, and my sponsor, the Chaos Give the Student Program, for their support. And I would really appreciate the guidance and the many skills that I learned during my time at the Carnegie Mellon University. Thank you very much.